G'day all, welcome to another CUDA toot. So we're going to sort of skip through a bunch of things today and hopefully get to coding something simple at the end. There's an awful lot to CUDA, but I think we should just get to coding as soon as possible. So yeah, alright, let's get started. Build customization. Yeah, you've got to add the CUDA 5 build customization to your project, otherwise Visual Studio won't know what to do with the CU files, .cu. We code CUDA C in perfectly normal text documents or source code files that we add to our project. We give them the .cu extension so that Visual Studio knows to give them to the NVCC compiler, which is the NVIDIA CUDA C compiler. And that compiler is actually going to compile the CUDA C code to PTX assembly and embed that in our exe. And then when we go to run our application, that's actually going to get compiled to specific machine code for whatever device we happen to have in our system. It's really quite clever. Okay, so headers and libraries. Yeah, we've got to include CUDA.h header in the .cu file, and we've also got a link to the CUDA lib file, the library, the main CUDA runtime library. That's going to appear as something like this in the linker, additional dependencies. Yeah, $CUDA toolkit libdir / CUDA.lib. We'll do all this at the end in a demo so you can see what it all means. Yeah, there's a few directories that you might want to include as well. So in the additional headers directory or the additional libraries directory, you can put in the place where the main CUDA headers are and the libraries directory. There's 64-bit libraries as well. If you're using a 64-bit system, maybe you want to try that. We'll just be making a 32-bit file mostly. Okay, so onto some terms. The CPU is called the host and the GPU is called the device. A kernel is a function that's written to be executed on the GPU. So the kernels are the actual CUDA C code that we write. And usually a kernel is executed hundreds or even thousands of times at once, all simultaneously. And basically CUDA C is all about writing these kernels. CUDA C is pretty much the same as regular C, only there's a few restrictions. So the kernel functions that we write are written in CUDA C, but you can't use recursive functions. They return void, and you can't use a variable number of arguments, and they also don't have access to the system memory. Yeah. Okay, function qualifiers now. We designate functions as kernels by placing function qualifiers before its name. So if we put global beside a function that we write, that's a kernel. And global means that it can be called by the host, but it's going to run on the device. So when we write a CUDA kernel, we put global at the start, then we call it from the host, and it runs on the device on lots of little threads at once. There's also the device qualifier, and this means that it's called by the device and it also runs on the device. So this is for kernel helper functions, just little external functions that you might have written that help a kernel calculate whatever it needs to calculate. You can also have perfectly normal host functions. I mean, we're not writing whole programs here on the GPU. The GPU can't run whole programs. So if you put host beside a function in a CU file, it means that it's a perfectly normal CPU function. And the NVCC compiler is actually going to give that back to the Microsoft C++ compiler, so that the normal C++ compiler can deal with regular C++ code. Alrighty, yeah, you've got to copy data back and forth from the GPU. The GPU can't see system RAM, and the CPU can't see the GPU's DRAM, the on-chip global memory in the GPU. So you've actually got to copy data back and forth between the two. The flow is basically you copy data from the CPU to the GPU, then you have the GPU work on the data with its kernels and its threads. Then you copy the answers that it comes up with back to the system RAM. And we do all this copying, this memory management, using some really useful functions. And yeah, we'll just go through them. So CUDA malloc is the same as C's malloc function. that just allocates memory on the GPU. You just pass it a device pointer, which actually looks exactly the same as a host pointer. So there's actually naming conventions and things that you should probably abide by in order to, you know, not lose track of which pointers are for the host and which pointers are for the GPU or the device. Anyway, the second argument is how many bytes we want. Do keep in mind that the GPU has, you know, a lot less memory than the system RAM. So maybe the GPU has 1 gig, or if you've got a really high spec card, maybe you've got more than that, but the system RAM might be 6 or you know, usually the system RAM will be much more. But the system RAM is slower than GPU RAM. Anyway, this function reserves memory on the device. Okay, the next CUDA API function that we're going to look at is CUDA free. And once you've allocated RAM on the device, you should always free it after you're done with it. So that's what we do with CUDA free. You just pass it the device pointer that you want to free, and it works exactly the same as the C free function. Okay, here's another function. This is CUDA memcopy, or memcpy. We give it a destination and a source. They're both pointers, and a size in bytes that we want to copy, and then the direction. This is used to actually copy data from a pointer on the host to a pointer on the device, and vice versa, from the device to the host. And we tell it which direction we're actually copying with this direction thing here at the end. So we'll put either CUDA memcopy device to host to copy from the device to the host, or CUDA memcopy host to device to copy the other way. Okay, that's good. That's good. Let's get to coding something. We're going to get the GPU to add two integers together and tell us what the answer is. If you timed it, you know, the CPU is going to do this hundreds of times faster. This is not really a good use of the GPU, but it's a good example of how to use some of these, you know, basic functions. So this is what we're going to do. We're going to create two integers for the host, just perfectly normal C++ variables, and then we're going to allocate some memory to make copies of them on the device. Then we're going to copy the values of those integers to the device's memory so that we've got two copies of exactly the same variables, or exactly the same values. One will be in the host and the other will be in the device. Then we're going to call the kernel to add them together. We'll look at, you know, threads and exactly what a kernel is and all this sort of stuff later. I just want to dive right in and make something small today. But after we've called the kernel that actually adds the integers together on the device, we're going to copy the results back to the host and print out the results just to make sure that the GPU actually knows how to add two integers together. And the final thing that we'll do is free the device's memory. Yeah, we said that already. That's stupid. The final thing, before we get to coding, is the kernel launch syntax. So when you actually call a kernel from the CPU's code or the host's code, you give it these triple chevron or triple triangle brackets, and inside you put the numbers. Now these numbers are actually the number of blocks and the number of threads per block that you want to run, but we're just using 1 today because we're being silly, and this is going to be terribly wasteful on the GPU, but yeah, it keeps things simple. So we'll get into exactly what these numbers mean and how we can do amazing things with them later on. Anyway, they're called the launch configuration. Okay, so that's the end of the slides. Let's jump over to C++ and get to coding. So I'll just file, new, project, and I'm going to choose empty project, and I might type here CUDA shoot 2. Hopefully that's not taken. Yes, it is. CUDA shoot 02. How do you like those bananas? Yeah, good. Okay, so we've got a new project. I'm just going to get rid of these stupid headers. No, directories, because I don't like them. Sometimes I do like them. Alrighty, so the first thing that we'll do is add the build configuration. If you right click on your project name and go to build customizations, you should see one of the options here is CUDA5.targets.props. If you can't see that, then you've not installed CUDA properly. And yeah, go back to NVIDIA and download it again and install it. Anyway, I'm going to check that box. You mightn't have the CUDA 4.2. That doesn't matter. We're looking at CUDA 5 now. That's the newest one. And we click OK. So that's now going to route all of the files with .cu extensions through the NVCC compiler, NVIDIA's CUDA C compiler, before it gives them back to the Microsoft compiler to compile the regular C++ stuff. Alrighty, let's add a file. So add a new item, and we want a C++ file, but we're going to give it the .cu extension. I'm just going to call it main.cu, so just remember that .cu extension, and we click add. Okay, now we've basically got a file that we can put kernels into, and we can also put perfectly normal C++ stuff. So we're working with the console window here, just to keep things simple. Include CUDA.h and IOStream. Okay, so we've just included a few things. I might actually add the libraries and the directories for this header just here. I'm not sure if it's set up to know where CUDA.h is. It should be, but I think it's not. Anyway, if we go to properties, you want VC++ directories, and right here you should see include directories. We've got to add the CUDA headers directory. So if you click on the little new here and then the ... I think they'll be in the same place on your machine as mine. So if we go to local disk and then program files x86, if you scroll down a bit, you'll find there, NVIDIA Corporation. You know what? I'm in the wrong place. It's program files. It's not program files x86. Alright, scroll down a bit. Here it is here. NVIDIA GPU Computing Toolkit. Okay, double click on that, and then we go to CUDA and version 5. And you'll see the include directory just there. Click on that and click select folder, and then OK and apply. Okay, so that tells Visual Studio where it's likely to find CUDA.h. The other thing that we've got to do is add to the linker and input. We want additional dependencies right here, and $CUDA, what is it? Toolkit libdir. Alrighty, I just typed $ and then in brackets CUDA toolkit libdir, or that's the macro for the CUDA toolkit library directory, and then the actual file that we're including from that directory is CUDA-rt.lib. Yeah, I don't know how well that's going to come out in the video, but I hope you can see that. Anyway, then we click apply. I don't know that the library directory is actually included as well, so maybe we better include that. If we come up here to VC++ directories, we go to library directories. You might want to include the actual directory that has that file, otherwise it might have trouble finding it. So once again, we go to the C drive. It's program files, it's not program files x86. Scroll down till you find NVIDIA GPU Computing Toolkit, and then CUDA version 5, and you should see lib just there. If you're making a 64-bit application, you might go x64, but today we're just sticking with Win32, so I'll double click on that and select folder, OK, and apply. Alrighty, well that was pretty painful. We just included the directory and libraries. Good. Let's write a kernel. Global. So this is a kernel. I put the global function qualifier right there. Add ints CUDA. Okay, it's just going to be called add ints CUDA. It returns void because that's just what kernels do, and it takes two pointers, A and B. So most of the stuff that you end up doing with the GPU is done with pointers. Anyway, A0 plus equals B0. So we'll just add those, you know, whatever the ints those things are pointing to together and store it in A. Good kernel. Okay, int A equals 5 and B equals 9. Alrighty, so in my main method I've just declared two perfectly normal C integers. A is set to 5 and B is set to 9. And right there I've just made two pointers, but these are actually going to be device pointers. They're going to be device pointers to the values that we copy from A and B on the host, and yeah, they look exactly the same as regular host pointers or regular C++ pointers. To differentiate between host pointers and device pointers, I put a D and an underscore for device pointer. Yeah. Alrighty, we call CUDA malloc. 7 DA. Alrighty, we want to allocate exactly one integer worth of data on the device with this pointer, and we want to allocate exactly one integer worth of data for this pointer as well. I want to mention that we should also be checking here for CUDA success. You know, and if these things fail, we should be, you know, quitting the application and having an error message, but we'll get to all that stuff later. Alrighty, so all we've done is allocated two integers on the device, and these are pointers to them. The the host doesn't know what these pointers are. If you try and, you know, store stuff in those pointers, the host has no idea. They're device pointers. Okay, CUDA memcopy. Alrighty, so now we're copying. The first parameter is the destination, so that's the D underscore A, and the second parameter is a pointer to the source. So all we're saying really is copy the value 5 from, you know, the host to this pointer just here on the device. It's an integer, that's how big it is in bytes, size of int, it's going to be 4. And then we put the direction, so we're copying from host to device here. Might just copy that, and we'll do the same thing for the B integer, and there we go. So now we've copied both of these values, 5 and 9, to the device. Hopefully they're sitting on there nice and happily. Now we can do the really cool thing, and that's actually call the kernel. We give it the triple chevron there, the, what do you say, launch configuration. And we pass it the two pointers, the two device pointers. It's no good passing host pointers to the device, it doesn't know what they are. Anyway, that is going to call this kernel with one thread, acting in scalar. If NVIDIA could see this, they'd be so upset. But we're using their beautiful GPU to do a single thread. Yeah, good stuff. Alright, once we've done that, so it should, the GPU should have added those two integers together and store the answer in D underscore A. All going to plan anyway. So we'll call that again. A and D underscore A. Size of int and CUDA mem copy device to host. Alrighty, so once the GPU has actually calculated that addition, we want the answer back from it. So we'll copy from its D underscore A pointer into our A variable, which we can then print out. The answer is, drumroll, A and all. The answer is A and all. Okay, I'm going to put a breakpoint down here. We better free the memory that we allocated before as well. Okay, so there's a pretty small chance that that's actually going to work since there's no IntelliSense and I have no idea what I just typed. Let's just give it a play and see what happens. Oh, it did work. Hey, there it is. Look at that. The answer is 14. That's unbelievable. 5 plus 9 equals 14, according to the GPU. Okay, well, that was a complete fluke that I didn't have a typo in there, but that's really poor use of the GPU, but I hope that that was a pretty good introduction to just a few little things, such as copying memory to and from the device, and also calling a kernel. And next time we'll get stuck into, this stuff in a bit more detail. Launching more than one thread, and yeah, it's going to be good. Anyway, thank you for listening. See ya.